Hello everyone. Here we are again. This is video number 4 in our video series on the topic of industrial AI. I am Rahul from Tvarit, our expert on the data from Beckhoff, Fabian. In this video, we are going to talk mainly about the technology. This is meant for IT engineers, data experts, data scientists, as well as data architects. The topics we are going to cover in this video are mainly data acquisition concepts, as well as how do we ensure the data quality. Without data quality, all AI initiatives fail. So let's get started. Perfect. So I would like to then request to Fabian to take over the topic of data acquisition. Fabian, would you like to explain the concepts of data acquisition?
Yeah, sure. So the basis of all AI projects or AI initiatives is, of course, high quality data. What does high quality data mean? So, for example, this means complete and structured data. This is very nicely possible if you use the right TwinCAT tools for collecting the data, because they are by default then structured and complete, because we use the right techniques to, in every cycle of the PLC task, push out the data and store it in a structured manner. On the other hand, high quality data also means that they need to be computer readable in a non-proprietary format. And this is also possible with all of our products. Maybe due to performance reasons, we log in a proprietary format, but we also always provide you the right tools for converting those proprietary formats into computer-readable common formats. For example, as indicated here, the TC3 scope export tool, which is an executable that you can run. Either you run this manually as a user, or maybe you're aware of this function block ntstart process that can also be used to run the executable in the Windows user mode triggered by the PLC. Also, data needs to contain context. Context means that you add more meta information to a certain value. If you hand over only a table of values, 42, 43, 45, 45 dot point or 2 or whatever, and you hand this over to Rahul, Rahul will say, hey, that's nice, but I have no idea what it is. Is it degrees Celsius? Is it a flow rate? Is it whatever? I don't have any idea about that. So always add meta information to your data. And of course, you can do so in many different ways. For example, with a scope, add a unit, or directly insert meta information in the PLC by using structured data like a data type combining an integer and a string, where you can place, for example, a JSON string. Also, if you talk about data collection, what is very, very necessary to my understanding, that you control the data logging directly from the PLC. So of course you can connect from an external device like a client to the TwinCAT runtime, and then start, hey, I want to have the data, which is basically what you do when you use a scope view client to connect to your TwinCAT runtime. Click on a button record, click on a button stop, and then export it as a CSV file, for example. This is possible. It's a quick shot. That's nice. But if you directly control the data logging from the PLC, you can trigger data logging based on process start and process stop. The timing is always defined by the control logic. And if you implement the logic of start, stop, and save also in the PLC logic, this makes much more sense. So you should be aware of those function blocks down here, like the scope server control for controlling the scope server from the PLC, or the PLC DB commands for controlling the database server, or the interface to the analytics stream, which is an interface to the analytics logger. Using those tools, you have full control over of your data, why you or how you communicate, and also how you store it. And what to do then with the data, that will be explained by Rahul.
Yeah. Perfect. So you have the data. You have the data with you. What do you do with this data? How easy is it? How easy is it to create an industrial AI model and deploy it in your shop floor, in your machinery, and get benefit out of it? There exist two philosophies, two methodology probably we can say. One, you have the data. Data is your input X, output Y. Machine is going to break down, let's say that is your Y. Yeah? You have this X and Y. This is the data. Using machine learning, deep learning, you learn what is the model using this X and Y. Now, the second approach is essentially you have a model beforehand, a model of a specific process. And now what you want to do is you want to simulate machine breakdown, or you want to simulate, let's say, quality defects. This is the second philosophy. First one is readily used by all AI experts, also even the IT engineers, data architect, data scientist, all of them are pretty aware. That is the philosophy number one. You have data, you have to create model. But the question is that sufficient? And the answer is no. In case of industrial AI, we need to mix this philosophy number one with the philosophy number two. What in this process, what we are doing is we are mixing the AI concept with the simulation related concept. And that's what being shown here in this particular diagram. Here you can see, apart from the real-time AI methodology, data-driven methodology, it's also very, very important to do a physical or chemical simulation of your process. And statistics point of view, you try to simulate the breakdown, or you try to simulate the defects depending upon the use case. Once you have these two, then you fuse both of these this knowledge together in order to bring a great accuracy model. Let us understand very briefly how does it look like on Tvarit industrial AI software. Perfect. So the Tvarit industrial AI software, what exactly is it? I'm sure all of you IT engineers, data architects, data scientists, one thing which we all love, by the way, I myself have been a data architect earlier and also a data scientist. I have lived the life of an data expert / IT engineer. I know the pain we have when integration fails, when the integration between our script number 1, script 2, script 3 fails, and you start debugging, but you do not know where exactly is the problem. And that has been one of the motivation behind coming up with this industrial AI framework. In this framework, what you can do is, you can essentially straight away go ahead with machine definition in step number 1. Step number 2, you can define all the parameters. And then finally, you can run the industrial AI jobs. These jobs are nothing but AI algorithms. Here, also very important thing is the machines. One unique thing about hybrid model approach is also that you can also keep storing these industrial AI models, which are the ready-made AI models corresponding to the specific type of machines. If let's say the machine is welding machine, or it can be sheet metal cutting machine, die casting machine, or hot rolling mill machine. There can be all different types of machine, and all these types of machine can be stored here as an asset repository in our framework. This is one of the biggest uniqueness, and corresponding to each machine, we are also doing research on bringing these industrial AI models off the shelf. These can be also used by our users. If let's say the IT engineers or data architects, the IT people, if they are not coming up with this background of process simulation, they can still seamlessly utilize the ready-made models available. If we look at this step number 2, parameters. Once you have selected a machine, let's say a welding machine, in this welding machine you have let's say the pressure inside this machine rotor speed, temperature, humidity, etc. These are different type of sensoric parameters we have to measure. And in these parameters, we have to see what is the variation happening corresponding to these variation. We also have to then find out a pattern with machine breakdown or quality defects. And that now brings us to the step number 3, jobs. And here, essentially, we can select different kind of tasks. We can select task for a given specific machine and a given specific parameter. For example, output parameter, we run the jobs such as training the module, prediction, or even root cause analysis, prescriptive analytics. After running all these modules, the results are going to be available directly in a dashboard format. Here, if you click on this output, you will be able to see the results simply directly in the dashboards. These can be directly integrated with Tableau, Qlik View, etc. Once the model is done, now let's talk about deployment. Perfect. So for deployment, I would again like to invite Fabian. Fabian, maybe you can explain a little bit about Onyx framework.
Yeah, thank you, Rahul, for the very nice explanation of Tvarit Industrial AI software. I think maybe some of you already know Onyx as a description file. For maybe I want to get a few words on the basic ideas of Onyx and why is it used. So Onyx, for example, first of all, is an abbreviation, of course, which is Open Neural Network Exchange. The basic idea of Onyx was to have a common file format for all different AI frameworks like PyTorch, like TensorFlow, Paddle, and MXNet, and so on. So there are so many different AI frameworks in the field. And then out of a sudden there was an idea, hey, we should somehow have a common file format to export a learned, for example, neural network from PyTorch and then import it into TensorFlow. And this is one of the key elements of, for example, transfer learning. So you train something in your framework like PyTorch, you export it as an Onyx file, you publish this Onyx file somewhere, and other users can import this Onyx file in their beloved framework. So they can stay in the environment that they are used to, and it's the key of interoperability between different frameworks. It's not only interoperability between frameworks, but in the end also interoperability between different inferencing machines. So, and that's why we as Beckhoff chose Onyx as our common file format for reading in already learned models into our TwinCAT inbuilt inferencing ecosystem. So, and basically what you do is you use the Onyx file. If you use a PLC-based hard real-time inference from Beckhoff, you need to convert this upfront into a proprietary file format and then can load it into a function block and then run the inference. That's the basic idea. But first, before we focus more on the deployment, let's also focus on a very necessary step in front before you finally deploy your model in the field, which is test and implementation. Suppose you have now a learned model and you want to integrate this into your TwinCAT environment. You can, of course, do so. You can write your PLC code, integrate this into your TwinCAT source code. But I really want to highlight that this is a data-driven model, and you should test this very carefully upfront. And so, and do this in a safe and also virtual environment. So the best way in our thinking is to, first of all, use a test database and stream the data that you want to test into the TwinCAT environment, and then use this in-streamed test data for evaluation of the model that is now implemented in your TwinCAT environment. Such you directly have the production code. It's production code. It's pure TwinCAT PLC code, but you test it with your test data set. And only if this test of your implementation is successful, then you should go step forward and implement this directly on the machine. And this can happen, of course, in different ways. Like I think most of you know, we use PC-based control, and PC-based control basically means scalability in performance. So we can start with Intel Atom-based controllers and go up the complete row over the Intel Core I series and with the Intel Xeon processors. Because we also build our server cabinets, you can also use hardware accelerators if you like to run the models on these accelerated platforms. What kind of software do we provide for implementing all those? On the one hand, we have a PLC integrated inference engine, which means that it's running in hard real time. We don't need additional hardware for it because it just runs on the standard CPU that you already use for controlling, for the PLC, for your NC task. And for this, we use selected and highly optimized AI models. So as of today, we support, for example, multi-layer perceptrons, support vector machines, the random forest algorithm, and k-means, currently working on PCA, and also upcoming algorithms like CNNs and LSTMs. But those are very selected and highly optimized. And on the other hand, we have another inference engine, which is PLC interfaced. This runs in near real-time execution, not directly in the hard TwinCAT cycle in the real-time tick, but we have access to high AI optimized hardware options like big GPUs, big server CPUs, and scale over dozens of CPU cores. You can use also integrated GPUs for execution, and you don't have the selected high optimized models, but you have the full bandwidth of all AI models in this inference engine available. As depicted here, you could either use an edge device for that and have separate devices, like one for control, one for inference. But of course, you can also implement this all on one device. So just scale, for example, to an Xeon D-based CX module, have full processing power, so that you have then the Xeon D CPU power, and also the graphical unit available on this controller for running your AI models very near real time to our hard TwinCAT environment, the real-time environment. If low latency is not an issue and you may only have a unidirectional data transport, so transport is only going to the inference engine, but no reaction is required in the machine. Also, cloud deployment is, of course, an option, and you end up in something like AI as a service. You connect your machine using our TwinCAT IoT or database products to a cloud infrastructure and run then the inference on this infrastructure. Okay, a small recap on this fourth video. So first of all, we talked about data acquisition using different kinds of TwinCAT products. We also talked about the possibility of using the PLC function blocks for interacting with the data logger and what the pros of this concept is. We also have learned from Rahul the model training using the Tvarit industrial AI software package. We learned about the evaluation model in production code using TwinCAT to stream in test data sets in your PLC and test your function implemented, the inference engine in the PLC. And in the end, we also talked about different deployment strategies in the factory for using, basically TwinCAT product families. Okay, so that's the end of the fourth video. Thank you very much for watching. If you have any questions, don't hesitate to contact us under Beckhoff.ai or Beckhoff.com, and of course Tvarit.com.
Thank you. Thank you very much from our side as well. Please do let us know in case if you would like to have access to our demo, access to our TIA software. Thank you very much.